Today you are going to see a lecture on click chemistry. I spoke first introduction lecture regarding the bioconjugation as well as atom economical reaction. So, click chemistry also is an atom economy reaction and which was developed by Professor K.B. Sharpless, who was a Nobel laureate, and so K.B. Sharpless he developed in basically around 2003. Okay. So, and it was only a for synthesis of small molecules, the triazole molecules, to synthesis of triazole molecules. That is the click chemistry. So, why it is called click? Okay. So, it says click. Okay. Say click chemistry. Why it is called click chemistry? It is so reaction is synthetically very appealing, high yield, very simple reaction conditions, and tolerance of moisture, oxygen, and very simple product isolation. So, this is the advantage of click reaction. And I will give you a small overview of the click chemistry. Let us go out and do the next one actually. So, he has reported in 2003 in Chem Biochem. Okay. So, in Chem Biochem was reported, Chem Biochem was the journal was reported by Professor Sharpless, and 2003 in volume number was 3 and page number was 1246. Okay. And why it is important in biology? Okay. So, it is an organic reaction. Why it is relevant? Okay. Whatever happens in biology is chemistry, as I talked to you before in the some of the organic chemistry classes. So, whatever happens in biology is chemistry. So, let us say this chemistry is used for bioorthogonal reactions. What do we mean by bioorthogonal? So, bioorthogonality is the main criteria if you want to conjugate any two biological molecules. For example, you have a carbohydrate, plus lipid. We want to link these two, want to study the effect of the lipid conjugation with the carbohydrate. How will you do it? This is one of the challenge, because carbohydrate has nearly about 6 hydroxyl groups, and lipid you may have a fatty acid, maybe having only one of the COOH. Okay. But specifically linking the lipid to any one of the any one of the hydroxyl group is a challenge. So, how do we do that? That is possible if we are able to perform click chemistry with this actually. Okay. Click chemistry is nothing but a reaction of an azide with a olefin leads to the formation of triazole. Okay. So, leads to the formation of triazole, and if you look at the structure, please look at how I am seeing it. See here, I have written R1. Okay. The R1 comes here. Okay. This R comes at this place. So, you please have the regiochemistry done properly. So, this is what is more important to know about this one. So, why? So, the first class I also talked about orthogonality, correct. So, sorry, why was I talked about the bioorthogonality. So, why is bioorthogonality is important? You take a protein, protein has very different functional groups. It has carboxyl group, it has amine, it has amide, it also has hydroxyl, it also has thiol, guanidinium group, in arginine, all of them are present. So, in protein you have several functional groups, several functional groups, as I mentioned before. Let us say you have a huge protein, in that you have, let us say, one position you have a lysine, or to simplify it I will put a serine, Now, you want to attach a fluorophore, to study the interaction of this protein with another macromolecule like DNA or another protein or protein 2 using a spectroscopic method. How will you exactly attach at particular point of this one a fluorophore? Because you have several functional groups in which, as I mentioned you before, it has carboxyl group, it has amine, it has thiol, guanidinium group, amide, etc. in a protein. How can you make it this OH to attach to the fluorophore and make it specific reaction? There is a possibility, if you are able to convert this protein, or if you are able to attach the fluorophore, we have a fluorophore with an alkyne, and let us say you convert this OH into this OH into the azide, Now, when you react these two, the azide, when you react this fluorophore with this modified protein, these two will react specifically, because there is a specificity between these two functional groups. So, that is why we call it bioorthogonality. No other functional group like acid, amine, thiol, guanidinium group, nothing will get interfered in the reaction of between the reaction between the azide and the alkyne. So, that is the beauty of the click chemistry. So, the first introductory class I also talked about addition of thiol to maleimide or addition of thiol to the alpha beta unsaturated compounds like chalcones. So, in that case for example, in this case the protein we have a SH, okay. As a protein we have a SH, and if we have a fluorophore, which is linked to maleimide, that is what I talked about in the first class. This is a maleimide. So, like similar to the reaction between thiol and maleimide, which is a bioorthogonal, the reaction between the alkyne and azide is also bioorthogonal. So, they are very specific in the case of reactivity. Whenever maleimide is present, the thiol reacts to lead to the formation of, we have the thiol, okay, linked to, basically we have a this is a fluorophore. It is a fluorophore. Here hydrogen. So, this reaction is atom economical reaction. This reaction is atom economical reaction. Similarly, the reaction between the azide and the alkyne is also atom economical. I would like to stress again what is an atom economical reaction. Whatever the atoms present in the reactant 1 and reactant 2 will be present in the product. There is no byproduct including water. Even water is not released. So, whatever the atoms present in the reactant 1 and reactant 2 is present in the product. So, even there is no byproduct at all. So, this kind of reactions is very well wanted because isolation is easy. You do not need to purify your resultant product, and it makes it attractive for the chemical biologists to unravel the biological pathways. So, similar to the addition of thiol to maleimide and reaction between alkyne and azide is also an atom economy reaction. Okay. This is the reason, and apart from this, making of triazoles is also advantageous in terms of medicinal chemistry. So, people like to explore making various triazoles to synthesize. So, this is one of the easiest way of doing the reaction actually, okay. And this is why we are performing this experiment, and I do not want to, although it is an online lecture and everything, and you need to take proper precaution in doing the experiment, and without supervision you should not do any of this experiment, and azide is little dangerous, and and also you may if you, because of azide in nature, it releases the nitrogen, it is highly explosive in nature, you need to be extremely careful in doing your reactions and doing it actually. Okay. So, now let us see that what the reaction we are planning to do. Okay. And the reaction we are planning to do is the reaction between simple alkyne and phenylacetylene. The reaction we plan to do is, we have a benzyl azide, we have the benzyl azide, we have benzyl azide and para para-toluene acetate. Benzyl azide, this is the benzyl azide, this is, we can say, para-methyl phenylacetylene, phenylacetylene. So, you react in the presence of cupric sulphate. Cupric sulphate is always hydrated, we have a water molecule is present, and sodium ascorbate, tertiary butanol and water, one is to 1 ratio. It's about 60 degree Celsius. Okay. So, what you end up having is this is the product. This is the product you will get. So, the reaction is very easy, and you do not do what you need to do is, in a reaction flask you have to take both the reactants in the tertiary butanol and water, and so the mixture of tertiary butanol and water is pretty important, because tertiary butanol and water are miscible, and tertiary butanol makes it solubilize both organic compounds, and water helps in solubilizing the copper sulphate and making the reaction medium, and sodium ascorbate also increase sodium ascorbate also, it improves the solubility. So, temperature is little required to do the reaction. So, you will get this product in a colorless solid, and you will see that very easily. As we mentioned in the previous for the synthesis of chalcones, the progress of the reactions or the completion of the reaction need to be monitored by TLC, and I will again reiterate, basically you need to have 5 TLC plates, okay. You have the line drawn in the bottom, okay, and you put 5 different spots, because each time I reiterate, because it is important, because the second time, so I am reiterating the same thing. In the lane 1, I will put lane 1, 2, 3, 4 and 5, okay. The lane 2 and 3 will contain the reaction mixture. Lane 2, 3 and 4 will contain the reaction mixture. Lane 1 and 2 will contain reactant 1, lane 4 and 5 will be co-spotted with reaction 2. That means in spot 3 you will keep only the reaction mixture, in spot 4 you will put reaction mixture and reactant 2, and in the spot 5 you will put only reactant 2. Similarly, for the spot 2 you will put reaction mixture plus reactant 1, and at spot 1 you will keep only the reactant 1. So, this ensures that there is, you can monitor the reaction, you can find out that any product is there or not there, very clearly you will find out. For example, you have reactant 1 benzyl azide, let us say it has, I do not know its RF value,
0.5, benzyl is 0.9.
Eluent.
Hexane ethyl acetate 20%.
Okay. So, the elution was done with 20% ethyl acetate and hexane, 20% hexane, and the benzyl azide is about 0.9, okay. Let us say this is about 1, and the benzyl azide may come at the 0.9 like this. So, since we are co-spotting here, you will also see the co-spotting here, and phenylacetylene is much more non-polar, am I right?
Yes, sir.
It goes to the top.
Just above.
Yeah, phenylacetylene is little bit non-polar than that. So, obviously phenylacetylene will go much topper than that. So, you will see that phenylacetylene, so almost on the top, and here also you will see it, because you are co-spotting with the reaction mixture. On the reaction mixture, if you are seeing the reaction is incomplete, you will see the spot for the phenylacetylene, benzyl azide, and also you will see the spot for the phenylacetylene. You also see this is the spot for the phenylacetylene if it is incomplete. Okay. And apart from this, the product, you may see it, actually, okay, at lane 3, So, when the reaction is incomplete, you will see both the phenylacetylene, acetylene also, you will see the azide also. When the reaction is complete, of course, you will also see the product in the lane 2 and 3 and 4. Okay. So, this ensures that without any ambiguity, you can see all the starting materials as well as the product, and by co-spotting them, even if they are coming very close, you can distinguish them. So, that is the reason we are doing the drawing the line and putting a marker and everything, so that you will spot at the same place, and it will be easy for us to, so that you will not spot it somewhere here and somewhere on bottom. So, that there will be a small variation should not be there. That is the reason we are drawing a line and we are putting a spot on each one actually. Okay. So, this is for our easy understanding as well as the doing the other things actually. Okay. This is how you monitor the reaction, and after the reaction means the completion of the reaction was ascertained, and the reaction mixture was diluted with 10 ml of water, 10 ml of water, followed by 10 ml of water, followed by addition of 2 ml of aqueous ammonia, that is ammonium hydroxide, aqueous ammonia. After stirring for 5 minutes, and the product becomes a solid. The solid was filtered through the Buckner funnel, and you can get the compound purified either by crystallization or anything. Because of the simple triazole structure, most of these compounds are isolated in a very good yield and also as a solid, and you will find it they are all the same. So, since they are all of them are solid, they can be characterized by doing the test tube method, as I talked about before, by a melting point. By checking, because most of the compounds are known compounds, by checking a melting point, you will find out the authenticity of the compounds, and you can verify that they are all good for the this one. So, this is you can filter it and air dry it overnight, and all of you know how to calculate the yield, and yield also can be calculated. So, this is based on you say take it 1 millimole of azide was taken, and of course 1 millimole of acetylene also taken. So, you will result in nearly 1 millimole of triazole compound. Okay. Reaction is almost quantitative. Yields are varying between 90 to 95% depending on the various conditions and everything. Okay. So, now all of you are requested to go through the this experiment was done using the reference is Journal of Chemical Education, The year was 2005, and the volume number is 82 and issue number was 12 and page number is 18332, if I am right, it is 3435. 1835. So, now you also please go through the supporting information on this article. is a must. You please go through the supporting information. It provides many details and your final exams will be based on the reading of entire supporting information. So, please go through the supporting information, the references whatever giving. So, all of this supporting information and the articles can be accessed through pubs.acs.org. So, what are the molecules we have synthesized? That is basically the supporting information. You will see NMR, you will see the NMR of following compounds. You will see NMR of following compounds. They are nothing but you will see the NMR of this compound, both proton NMR and 13C NMR. No, only proton NMR, only proton NMR. You will also see proton NMR for other two compounds. You see proton NMR for this, and you take it for the exam. You look at wherever the what do you call, you go through all the NMRs in the supporting information. Supporting information. What I want you to do is, you go through the NMR in all the supporting information, all the NMR. I would like to do one thing. You take it for your final quiz as a clue, as well as a question is out type of thing. Okay. I want you to find out, pinpoint in the triazoles where this hydrogen appears in the proton NMR, where this hydrogen appears in the proton NMR. Apart from this, wherever aliphatic thing you see, like this one and this one, where do they appear in the NMR? The values, you please tell the values, you please find out the values for the delta values, chemical shift values, chemical shift values of these protons. Chemical shift values of these protons, you please find out, and you need to assign in the NMR where this hydrogen and this CH3 and this CH2 appear in the proton. Okay. And for this information, you can look at the supporting information of this article, okay, and let us try to see are you able to achieve it or not. Okay. I will give a clue. For example, this CH3 may come around let us say 2 or 3, okay, and this CH2 will come as a singlet, and for one thing we will, the tomorrow things I will continue and doing the assignment of this one for you for only one of the compound, okay. I will show you the proton NMR and I will assign each one of it, but for the other cases you please, after I assigning, you also please find out where these protons may come, okay. So, I am just giving you out of the question, almost question is out of type of thing for the final quiz, and so knowing about the proton NMR, because proton NMR is the one we are using for characterization of these triazoles, and you need to know this some of these details. So, tomorrow I will show the NMR and I will assign the for these peaks. I am just giving you the clues, but you have to do for the other what do you call other compounds which is present in the supporting information. We have done the triazole formation using click chemistry. I took an example of a triazole NMR spectrum from the supporting information as I shown here in the reference. That is the Journal of Chemical Education 2005, 82, and volume 12 is issue number, page number is 1833236. And you please also, apart from going through the article, you also please go through the supporting information, whatever the literature reference we are giving to you. Okay. All these things are available at pubs@acs.org. So, this is the NMR spectrum is given in the supporting information. I am going to explain to you the NMR for this compound itself actually. Okay. So, you can see here the NMR spectrum between 1 delta to the nearly about 9 delta. Okay. You see there are peaks with the integration. Okay. If there is integration here is about 30,000, is about 1,800, 18,000 is about 9,700, is about 9,700 and etc. Okay. So, how do you look at, so if you want to find out that okay, I have got the compound or not, how do you look into the which are very characteristic peak for the triazole compound. If you look at for the very characteristic triazole compound, you will find that this is one of this hydrogen, this very characteristic for this one. So, very characteristic for this one. So, where the hydrogen will appear, that is one thing. Second thing is, after the compound is formed, you have to look for the signature peaks. The signature peak is, one is the olefinic or triazole hydrogen, that is this triazole hydrogen. So, other two are basically this CH2, which is another characteristic peak, and also you can look for this also present in the starting material, this will be present in the starting material, this alkane peak is entirely coming different, this is azide peak. So, where this and this will appear in the NMR. So, I am giving you example of this, and you please go through the other NMR spectrum given in the supporting information, and if you are asked to identify similar characteristic peaks of the different NMR, you should be able to do that in the exam. So, in this case, if you look at this one, so the bottom one, whatever you are seeing it here, 9782, I will say this only for one proton. So, now if you look at the entire aromatic region, this has 5 and this has 5, there are 10 aromatic region, including this there is a 11. If you if you calculate all of them, it is about 20,000, 7,000, about 10,000, sorry 70,000, 70,000, 10,000, about 20,000. This accumulates or accounts for basically for the 10 hydrogens. These 10 hydrogens basically corresponds to these 10 hydrogens. So, that means that this region corresponds to this both phenyl ring hydrogens, and this triazole containing hydrogen, which is for the one hydrogen which is present in the triazole. This hydrogen, it basically comes at this position, this for the one proton. Okay. And you will also see another about 5.8 for one proton, that corresponds to the delta value at 5.8 corresponds to the OH. And you see a 2 hydrogens, this is for the one hydrogen, this is for one hydrogen, this is for 2 hydrogens. The 2 hydrogens belonging to the benzylic, where you see this benzylic one, that is the benzylic hydrogens, that is for the 2 things. The way you also see 2 peaks which does not have no integration, which has no integration, which is about 3.3 and 2.5. This 2.5 basically corresponds to the solvent peak DMSO D6, contains a little bit of undeturated solvent, that is for the DMSO, and another one, the water present in the DMSO comes at between 3.3, that is water present in the DMSO D6 comes at the about 3.4 or 3.3, and this CH3 comes at 1.7 delta. So, now you accounted for all the hydrogens, the aromatic hydrogens, 10 of them comes between 7 to 7.5, and triazole hydrogen which is comes around 8, okay, about 1 hydrogen, and also you look at the OH which comes at 5.7, and you look at the CH2 which comes out 5.5, and this is basically not integrated. These two are belonging to the solvent and water present in DMSO-D6, and this CH3 corresponds to the CH3 is present in the quaternary center. Okay. So, I would like to do, please go through the other NMR spectrum, and you should be able to assign similarly for every one of them which is present in the supporting information. So, this concludes the second experiment for the synthesis of triazoles or the Crick reaction. Okay. So, which is a very simple way of making a heterocyclic compound, and which was used for the many bioconjugation reactions also. Okay. This concludes the second experiment. Now, let us move on to the third experiment. The third experiment is basically isolation of curcumin. So, why people want to isolate curcumin? So, why it is important to isolate the curcumin?
Add 1 ml of tert-butanol and 1 ml of distilled water to a 20 ml screw-top scintillation vial and start stirring. One millimole of benzyl azide was transferred to the vial. Add 1 millimole of p-tolyl acetylene to the reaction mixture. 10 mol percent sodium ascorbate and 5 moles percent aqueous copper sulfate pentahydrate are added sequentially. The reaction mixture was stirred at 60 degrees Celsius for 1 hour. Progress of reaction is monitored using TLC. Once the reaction is completed, reaction mixture was diluted with 10 ml ice water, followed by the addition of 2 ml of 10% aqueous ammonia and stir for 5 minutes. The formed solid precipitate was filtered through a Buchner funnel filter and dried to obtain the corresponding triazole.